So let's move on from Lynette here. We can stop it. We can close that notebook. We are now going to work with AlexNet. So we're going to build another classic neural network. This one is quite a bit deeper. This is the one that we've talked about a number of times now, that in 2012 crushed the ImageNet competition and brought deep learning to the fore as this technique that everyone should be paying attention to. And we are now equipped with all the tools that we need to build it ourselves. So I already have the notebook fully built here for you in the notebooks directory. There's this AlexNet in Keras notebook working with the Oxford Flowers dataset. We are going to rebuild it from scratch here. It's sufficiently different from the Lynette notebook that we're not going to keep building. We are just going to get at it from scratch. So I'm going to give it a nice title here. Let's say AlexNet in Keras. And for me, this is a demo. Now give it a title. So this is AlexNet. And we can press M to make this a markdown cell. And we can say we're going to classify Oxford Flowers. And we're going to set a seed as before. So escape 4 to set a level 4 subtitle. We're going to set seed. And to do that, we're going to import NumPy and set the NumPy random seed to 42, as always. So of course, you can set it to anything you like for your own reproducibility. And we're going to load our dependencies. So of course, we need Keras for this. We are going to use the sequential model just as before. And we need to decide on all of the layers that we're going to be using. So I know that we're going to be using dense, fully connected layers. We're going to need dropout. We're going to need to flatten. We're going to have convolutional layers. And we're going to have max pooling layers. And we're going to want to do some normalization, some batch norm. We've talked about that, and we've seen and we've heard that it improves our results, particularly with deep networks. And boy, are we building a deep network now. Whoop, let's drop out doubled here. Whoops, models, spelling mistake. This is a capital D, getting sloppy. So then we need to load and pre-process our data, and we can do that in a single step here. So in the Docker image that I created for you guys, if you're using that, you will already have tflearn as well. Now tflearn is similar to Keras in many ways because it allows you to build models with a TensorFlow backend more easily. Right now we're just going to be using it to get these Oxford Flower data. We're going to use the 17 category set. So it should look like that. And these will already be pre-processed the way that we would like them. So we won't need to do any further pre-processing. We can simply load data here and specify that we want our outputs to be 1 hot, just like we had for the MNIST digits, so that every class, the 17 categories of image, is a 1 in the final layer, if that's the image being represented, or it's a 0 in the 16 other classes. So let's see how this goes. We are downloading the data, and in the interim, I can show you what some of these data look like. So I have them loaded on my machine here. We have all these categories, so categories 0 through 16, representing the 17 different categories, and within each one there are 80 images of a unique type of flower. So this first category is buttercups. I'm pretty sure those are buttercups. I am no expert. And then, so each category has these different images in it. And our neural network will be able to distinguish them. Despite that being, I think you can see that's a much more complex task than classifying the MNIST digits. So we have color, we have flowers of all different kinds of sizes, and while these data are loading, we can start to design our neural network architecture. So let's add another subtitle here to indicate that. We are still going to be using this sequential model. So all of our layers will simply feed into each other sequentially. And like with LeNet 5, we're going to start off with a convolutional layer in the first layer. It's two-dimensional. It's going to have 96 neurons or kernels or filters, depending on which word you prefer. And these kernels are going to be quite a bit bigger than they were with LeNet. So in LeNet, they were 3 by 3. In our AlexNet notebook here, they're going to be 11 by 11. So that's simply the size of the kernel that we're passing along the image here. So to be kind of more explicit here, we're now having 96 kernels, and this is 11 by 11. And this image size is actually different too. We're going to specify that in a second. I might as well do it while I'm over here at the whiteboard. So instead of being 28 by 28, it's going to be 224 pixels by 224 pixels. Our data have loaded and parsed. We're all good to go. We're going to keep building our network here. We have to decide on a stride length. So this is how far the pool moves. And so the steps are going to be a step of 4 pixels. That's how big each stride is going to be. And it's going to be 4 pixels in each dimension. So this 11 by 11 kernel will pass along, making jumps of 4 pixels at a time. And then when it gets to the end, it'll move 4 pixels up and continue along and continue repeating that until it's gone over the whole image. All right, so we're deciding on a stride length of 4 by 4. We're going to have activation ReLU, and here we specify our input shape is equal to 224 pixels by 224 pixels. And of course, now that we're using color images, we've gone from having just one dimension to represent here to having 3 different color channels to represent. So we now also have this third color dimension to work with. So that's our first convolutional layer. We've defined all of the parameters. We're going to add in max pooling to decrease the computational complexity. Our pool size is going to be bigger than before. These are 3 by 3 pools instead of 2 by 2 pools, but they are still going to move the 2 by 2 distance. So they're going to have a bit of overlap with each step that they make. We're going to add in batch normalization to avoid covariate shift. And then we're going to add a second convolutional layer. It's going to be pretty similar to this first one, so let's copy and paste it. Some of the parameters are going to change, so instead of having 96 neurons, filters, kernels, whatever you want to call them, we're going to have 256 of them. And our kernel size is going to become a touch smaller. It's going to become 5. And our stride length is now going to be 1. So we can actually just not specify that parameter because the default is steps of 1. We're going to stick with that ReLU activation, and we don't need to specify the input shape here because we're not taking in from the input layer here. We're taking in from this first convolutional layer. The max pooling in this second convolutional layer is going to have the same parameters as in the first layer, so we can leave that as is. We're going to leave the batch normalization as is. And then now we're going to have a third, a fourth, and a fifth convolutional layer packed right next to each other. So let's copy a convolutional layer here. These aren't going to have max pooling or batch normalization in between them because that is how AlexNet was in 2012. We're going to have the same number of neurons, 256. Our kernel size is going to become a little bit smaller again. And now we're just going to copy and paste this 2 more times. So now we have a total of 5 convolutional layers. And we're going to increase the number of kernels in each of these 2 layers to 384. Then, after all 3 of those, we're going to put in a max pooling layer and a batch normalization layer. Once again, because that's how AlexNet worked, and it worked well. Now we're done with our convolutional layers, so we have 5. We want to pass those convolutional layers, which should now have some pretty abstract representations without any kind of spatial annotation. So the neurons just represent complex images on now a 3 by 3 pixel size. So we want to be able to recombine all 384 of those kernels that we have into any kind of combination to make, any kind of flower shape, really. So to do that, we need to flatten it because dense layers are one-dimensional. We went over that with Linet 5 already. Then we can add the dense layer. The dense layer in AlexNet has 4,096 neurons. And the activation isn't going to be ReLU for once. We're going to switch to Tanch because that seems to work a bit better here. Once again, these are just all kinds of parameters that you can fiddle around with yourself and see how it impacts your outputs. We're going to have dropout in this layer. So we're going to drop out half of the neurons on any given training step. And then we're going to do the same thing again. We're going to have another fully connected layer with 4,096 neurons, dropping out a different random 50% of those with every training step. Finally, we've reached our output layer. So for our output layer, as always, we have however many classes we are predicting. So we're predicting 17 different categories of Oxford flowers. And we have softmax activation here because we want to output probabilities. So let's run this cell. We got an error, and that's because I put my bracket in the wrong place. We don't want a bracket here. We want the bracket at the end. Very easy fix. And that's because I named this the wrong thing. It should be dense, not dropout. There we go. All right, that compiled. And let's look at the model summary. Now, Linet 5 had 1 million parameters. We have nearly 22 million trainable parameters in this model. This is far and away the largest network we've seen yet. This is truly a deep network, and just a few years ago, this was state of the art. Nothing on the planet could exceed its ability to correctly distinguish images. We're going to have the same compilation parameters here as before, so categorical, cross entropy. we've got our optimizer atom that we have been using, and our metric to track how we're performing is the same as before. Now we can train. So let's fit our model, an X, Y. Our batch size is going to be smaller now. We'd always been using mini batches of 128, but these images are so much bigger. The complexity of them is so much greater, and this network is so much more complex that we're going to have our batch size, so the number of images that we're training on in any given step, from 128 to 64. You can have however many epochs you like. We'll just set it to 1 to see if we have all of our parameters correct here. We want to see some output, so we set some verboseness. And we're going to do something a little differently here. So far, we had a validation set that was distinct. We split them up top. We split our X and our Y in our previous notebooks into training and test sets up there. But we're going to do things a different way here. Either way is totally fine. In this instance, we are keeping the training and validation sets together, and we're going to specify a new parameter here, validation split, to randomly select 10% of the data from each epoch to hold out and validate on that. We're going to shuffle, so we're not going to have the same validation split each time. And let's see if this runs. There we go. It's going. So this is going to take quite a bit longer than what we've been seeing before. 40 seconds, maybe a minute. This is a reasonably beefy machine with 16 CPUs. If you are using a GPU, this will be quite a bit faster. So after a single epoch of training, we have 12% accuracy, which isn't bad because we would expect 100 divided by 17 is 5.9%. So if we were guessing from these 17 categories at random, we'd expect to be correct about 6% of the time. And we have double that in our validation accuracy. So that's promising. Learning is happening here. And if you train this for longer, you'll see even better results. So after 10 epochs, I saw a 24% accuracy, so guessing right 1 out of every 4 times. And I got, after about 1,000 epochs, I peaked around 73%. Now 1,000 epochs is way longer than we had been training before, but that is merited in this situation because we have so many more parameters to tune. The images are more complex, the images are larger, so it can take more passes over all of the data to be getting good results. So AlexNet here is pretty deep and was clearly state of the art in 2012, winning the ImageNet large-scale vision recognition competition. But of course, networks today are even deeper. And just to demonstrate the kind of flexibility, the kind of modularity of this approach, I've also put together VGGNet, which was created by the folks at the Visual Geometry group at Oxford University, which we've already come across because they created this Oxford Flowers dataset. So we also have the VGGNet here that you can have a look at. It is quite similar to AlexNet that we had. So all we need to do is I'm going to save this, and then I'm going to make a copy, and we're going to call this our VGGNet in Keras demo. Change the title here to VGGNet. This is similar in many ways to AlexNet. It's simply deeper, and some of the hyperparameters on individual layers have changed. So with AlexNet, we had these parameters, and we're just going to make some small changes here so that we have 64 neurons in the first layer instead of 96, and our kernel size is always the second parameter here, so we can specify that simply with a 3. So a 3x3 kernel. Stride length is going to be the default 1x1, so we don't even need to mention it. Activation is the same, input shape is the same. That's going to feed right into a second convolutional layer with the same parameters, but of course we don't need to specify input shape because this is no longer the, taking the inputs. We're going to have a max pooling layer with a pool size of 2, and that's the first parameter, so we can simplify our language here a bit. We're going to use the default 1x1 strides, so we can strip out that parameter as well. We're going to keep batch normalization, and then we're going to repeat this convolutional structure twice. First with 624 neurons and 128. Keep max pooling the same. Oh, gotta get rid of this input shape. And then a few more convolutional layers. In total, we're going to have 16 layers in this very, very deep network. So 256 neurons here, and same thing for 3 convolutional layers in a row there. We're going to take this architecture and replicate it twice more with 512 neurons. And there we go. So our dense connections, our dense layers at the top are the same. Our output is the same. So we can leave that all the same. We're going to leave our compiling the same as well. So now we can reset our kernel and run everything. And it should just run. Indeed it does. So no mistakes there. Now, this network, adding in the more layers, now we have 34 million parameters that we're fitting. This ends up taking 300 to 400 seconds per epoch on a 32 core machine that I was using for this. And it gets about chance performance, 7% accuracy after 1 epoch. So with all of these epochs of training, we had 1,000 for AlexNet. We could have hundreds here for VGGNet. To be able to compare our performance epoch over epoch and really see what's happening, it starts to become way too difficult to eyeball the numbers by eye. So up next, we're going to use TensorBoard so that we can visualize all of our results epoch by epoch and be able to make some better decisions about our model building.